So we've reached the fourth stage of our mathematical journey. We've done some exploring and noticing, we've worked more systematically, and we've come to the stage where we've got some conjectures, we've done some generalising. But now, Charlie, we're here to make sense of the mathematics. Too often, perhaps, students go away with the feeling that maths is all about rules to be memorised. And what we'd like to offer are some representations that help them make sense of the mathematics and have understanding rather than need to rely on their memory.
So we're going to offer some examples, aren't we?
We're going to offer some examples.
Different contexts in which representations, some visual representations, but also an analogy later on, which can help students make sense of what's going on.
Absolutely. So let's start with a representation that is perfect for even very young children. So Charlie, very young children may be exploring what happens when you add odd and even numbers together. And they may come up with a rule, but we don't want them to rely on just remembering the rule. So let's think about a representation for an even number to start with. So you can see here I've used a block to represent 1. So we've got blocks paired in this way so that we can tell that this is a multiple of 2. This is an even number. Each individual block has a pair. Now, the dotted line in the middle is showing us that actually this could be any length. This could represent any even number.
So every square at the top has got a partner at the bottom.
Exactly.
Okay.
Okay. So by contrast, here we've got an image that represents an odd number. So we've still got these pairs, but we've now got one block which is on its own. It's unpaired, and this is an odd number. It's one more than a multiple of 2. Again, we've got the dotted line, so this could be any length. So we might like to think about what happens if we added together 2 odd numbers. So what I could do is I could represent another odd number and I could flip it over. So let's imagine that I take this odd number, and this time I'm going to draw it so that my single block, which is unpaired, sticks out here. And you can imagine, Charlie, if I added them together, I could push these 2 odd numbers together, and then the single block from the first odd number would be paired up with the single block from this second odd number, and then we'd end up with a representation like this, an even number.
And the value of this, it seems to me, that not only does it show me why 2 odd numbers will add up to an even, but it shows me that, well, any number of evens added together is going to be even. If I have an even number and I add an odd number, I'm going to get an odd. If I have 3 odd numbers, 2 of them would pair up, make an even, but the other one will give us an odd. I can also think about an even number minus an odd number.
Absolutely. And
all of a sudden, I'm going to have a square without a partner. I might start thinking about, well, if I have 100 of these, I might then think 100 odd numbers. I'm going to put them into 50 pairs. Each pair of these makes an even number. And so I'm going to get an even total, which means that if I have 101 of these, I'm going to have one odd one that doesn't have a partner. So it seems a really powerful representation because I can use it to answer so many different questions.
Exactly.
So students might be asked what 5 times 18 is. And we might expect them to have a visual representation where they're thinking of 18 crosses, 5 rows of 18 crosses, could represent 5 18s, but you could also think of it as 18 5s because you've got 18 columns with 5 in each. So I think I'm going to think of it like that. So that's the same as 18 5s. And I might think of the area of a rectangle representing the product of these 2 numbers. So I know that if I have a 5 by 18 rectangle, the area of that rectangle is the answer to that question. So I might be thinking about how to work out the area of that rectangle in order to work out the product of those two numbers. And one way of thinking about it, this is not very good to scale, unfortunately, is to think, well, I could split this rectangle into two halves. So 5 18s is the same as 5 9s plus another 5 9s. 5 9s are 45. 5 9s are 45. 45 and 45 is 90. So 18 5s must be 90. And that's one way in which I could be simplifying that problem by using something that I know. Now, that's not the only way. I'll try and do it more to scale this time. I've got 5 and 18. And again, I don't know quite how to do 5 times 18, but I do know that 18 can be split into 10 plus 8. So instead of working out 5 18s, I could work out 5 10s, which I know, and 5 8s, which I know. And so 5 18s is the same as 5 10s plus 5 8s. 50 plus 40 is 90 again. Here's a third way. I'm wanting to work out what 5 18s are. I'm not sure what they are, but I do know what 10 18s are. 10 18s are 180, but I've got two equal strips there, and the strip that I want, that one there, is going to be half. Half of 180, 90. So we want students to be resourceful, which means that they've got more than one strategy for working things out. The reason we can split this problem in this kind of way makes sense diagrammatically, and it gives students different options, different choices for how to approach this.
Absolutely. So I could use a similar area model, Charlie, I think, if I wanted to work out, let's say, 21 times 21. Now, I know already that 20 times 20 is 400. So I could draw a representation, as you were drawing, using the area model of 20 by 20, and I know that is 400. And if I'm trying to find 21 times 21, I can draw in an extra thin rectangle here, if we like. That will be 1 by 20. Similarly, below my square, I could draw in another thin rectangle, another 20, and then I'm left with this hole to plug, which is a 1 by 1. So if I want to find out 21 times 21, I know that it's going to be equal to 400 plus 20 plus 20 plus 1. So I think altogether that's going to give me 441.
And if you were going to do 22 by 22, what would that look like?
Okay, so 22 by 22, I could add on
Does that help?
I could add on another sliver here. And another 20 by 1 below. And this time, I would be left with 4 in the corner. So this time, I'm going to have 22 times 22 is going to be equal to 400 again. This time, I'm going to have 20 by 2. I'm going to have another 2 by 20. And I'm going to have a square of 4. So I think this time we're going to have 400 plus 40 plus 40 plus 4. So that's going to give us 484.
And without drawing, could you predict, can you describe what this would look like if it was 23 by 23?
I think so, Charlie. So I would know that we'd have our 20 by 20 square.
So we're doing 23 times 23. You can have a 20 by 20 square.
And then which we know is 400. I'm then going to have a rectangle to the right, which is 3 by 20. I'm going to have a rectangle below, which is 3 by 20. And then I'm going to have a 3 by 3 square, so I'm going to have 9 in the bottom right. So altogether, I've got 400 plus 120 plus 9, which I think is 529.
Can I do 24 by 24?
Yeah. So we've got 400 plus 80 plus 80
because that's
plus
4
60.
20s. I'm going to write 4 20s because that's similar to how you wrote that.
And plus another 4 20s.
For what happens underneath?
At the bottom. And then this time, bottom right, I'm going to be left with a 4 by 4 square, which is 16.
So I might write this as
3 squared.
3 squared. And I might write this as 1 squared. And I might write this as 2 squared.
Nice. We've got a lovely generalisation forming here.
So we're getting to, if I know that the area of an a by a squared is a squared, a plus 1 all squared when we get to a plus 1 all squared, we can use the images that you've been using to come up with the conclusion that the whole area is going to be a squared plus a plus 1 squared. And a plus 3 all squared, for example, I can picture the one that you were picturing here, with the a squared in the middle, the 3 strips on the right, each of length a, 3 strips below, so we're going to have 6a altogether. Right. And then in the corner here, we're going to have a 3 by 3. Yeah. And we can use this formula to check that we're getting the same.
So here, I guess, rather than relying then on a rule for expanding our brackets and multiplying brackets, actually, we've got a picture in our mind of what's happening here, which leads to much greater understanding than simply regurgitating.
I'm going to put you on the spot. A plus 10, all squared.
Okay. So I think that's going to be a squared.
The square in the middle.
Yep. And then I think we're going to have 20a, because I'm thinking about my 10 strips on the right, my 10 strips on the bottom. And then I'm going to have plus 10 squared, which is that square bottom right-hand corner, 10 by 10.
So this image, this representation of multiplication using areas of rectangles or areas of squares in this case, is incredibly powerful because it allows us to do so much and gives us that flexibility. We started by doing something that quite young students might do, and we finished making use of the same image, the same model, when we're working algebraically. These are the models, these are the representations which are really valuable to share with students.
So we may find that we're playing a game that involves 2 dice. For example, in Monopoly, you've got 2 dice, you roll 1 to 6, the 2 1 to 6 dice, and you find the total of the 2 numbers to determine how far you move on the board. And it may be that you've noticed, your children have noticed, that some totals seem to come up more often than others. For example, an 8 might come up quite often, whereas a 3 doesn't seem to. And we can think about a diagrammatic representation of our dice rolls to help us understand why some totals are coming up more than others. So if we represent, let's imagine we've got a red dice and a blue dice, just to distinguish them. We're going to represent our red dice on the horizontal axis and the blue on the vertical. And we can fill in the part of this diagram to show the totals of the two rolls. So for example, here we've got a 1 and a 1 on each dice. So this is going to give us a total of 2. And if we move horizontally to the right, a 2 and a 1 will give us a 3. And a 3 and a 1 will give us a 4, 4 and 1, 5, etc. going along that row. Perhaps we should just fill in a column or two. So here we've got the blue 2 and the red 1. So this is going to give us a 3.
And that's interesting, Liz, because you talked about a total of 3.
I did.
And these are the only 2 options. So a 2 and a 1, or a 1 and a 2. Whereas you talked about getting a total of 8. So...
where might we get an 8, Charlie, I wonder?
6 on the red.
And 2 on the blue. Right. 5 on the red. 3 on the blue. A 4 and a 4. And then the opposite way around, 3 on red and 5 on blue, and 2 on red and 6. Nice. So we've actually got 5 8s. So already, go on.
This might also help understand why it's easier to get an 11 than to get a 12. Because a lot of students think, oh no, there's only one way of getting 11, 5 and 6, and there's only one way of getting a 12, 6 and 6. So why are they not equally likely?
Why are they not equal? Absolutely. And so this makes it really clear, doesn't it, that to get the 12, there is only one possibility, a 6 on red and a 6 on blue.
Have I got this lined up properly?
However, for 11, in fact, we've got 2 ways. We've got a red 5 and a blue 6. But actually, we've also got a red 6 and a blue 5.
So 2 ways of getting an 11, only one way of
getting 12.
So representing the options diagrammatically like this makes it very clear what's happening. And it also means we could sort of start seeing that we're going to have sort of 7s here. I don't know whether I can line this up properly, but, and this is the reason why 7 is the most likely total. There are 6 ways of getting a 7. This is the longest diagonal. And then there are 5 ways of getting an 8. There are 4 ways of getting a 9. There are 3 ways of getting a 10. 2 ways of getting 11. 1 way of getting a 12. This sheds so much light on what's going on. And when students are working on probability, using a sample space diagram makes the situation a lot clearer. So Liz, some students are faced with a question like this, where they're adding and subtracting positive and negative numbers, and they struggle knowing what to do. So let's think about how we can help students understand what's going on. And I'd like to use an analogy here. So I'd like you to think about a football team. And you've got some positive players who score lots of goals. Mm-hmm. And you've got some negative players who score own goals.
Okay.
I want you to describe what you think happens if I add positive players.
Okay, so if I'm adding a positive player, I'm going to score more goals and my result is going to go up. I'm going to go up in the league.
So the effect is a positive effect.
Yes.
And I'm going to think of that as going up the number line.
Okay.
It's going to be a positive effect. Now, what happens if I add negative players that score own goals?
Okay, well, that is going to have, I think, a detrimental effect on my team's performance. So I'm going to end up going down in the league.
Okay, so I'm going to represent that with an arrow going down. So those are the two options where we're adding, either positive or negative number, but we could also be subtracting. Yeah. So I may subtract one of my positive players has gone off injured, for example.
Right, so I guess I'm less likely to score goals. I think this is going to have a negative effect. I'm going to go down in the league.
Okay, and what about subtracting a negative player?
Yeah, okay. So if I'm taking away my hindrance, if you like, then that's going to be positive. I'm going to go up. I'm going to score more goals, hopefully.
At least I'm not going to have own goals.
Exactly.
I'm likely to do better. So I'm going to be thinking about adding positive numbers or subtracting negative numbers as having a positive effect. Yeah. Same effect as going up the number line. Whereas adding negative numbers or subtracting positive numbers has a deleterious effect. I do less well. Yeah. So when I have a problem like this long one, I can be thinking of that. Adding positive 2 is going to take me up the number line. Subtracting a positive number?
Down.
Subtracting a negative number?
Will take me up.
Adding a negative number?
Down.
Subtracting a negative number?
Up.
Adding a positive number?
Up.
Subtracting a positive number?
Down.
Subtracting a negative number?
Up.
If we start at 6, add positive 2.
So that takes us up 2 to 8.
Subtract positive 4.
So that's taking us down 4 to 4.
Subtract negative 5.
That's going to take us up 5 to 9.
Add negative 4.
So that will take us down 4 to 5.
Subtract negative 7.
So that's taking us up 7 to 12.
Add positive 2.
That's taking us up 2 to 14.
Subtract positive 4.
So that's taking us down 4 to 10.
Subtract negative 6.
So we're going up 6 to 16.
Fantastic. So this model, and there are plenty of other alternative models, gives us a way of thinking about adding and subtracting positive and negative numbers, which helps to make sense of what's going on and avoids rules like 2 minuses make a plus. So Liz, we might ask students to give us a pair of numbers which add up to 12. So we might say, let's have x plus y equal to 12.
Okay, so for example, 2 and 10?
2 and 10 add up to 12.
Let's say 3 and 9?
3 and 9 add up to 12.
And
you could have 9 and 3.
I could say 9 and 3.
Yep.
I guess I might go for, could I use some halves, some fractional numbers?
Okay, if this first one's 4.5, can you have a...
I'd say 7.5.
Yes. If the first number is negative 2?
I'd say 14.
And you'd be correct. Are there many more?
I think we could go on forever, Charlie. I think there's an infinite set here.
So if I have negative 1,000?
Oh, I think I would need 1,012.
Okay. So I can carry on. I can make this as... What if I give you another challenge? I want the second number to be twice the first number.
Okay.
So I might write that as, if I think of coordinates, I might say that the second coordinate, the y coordinate, is twice the x coordinate.
Okay. So I might start simple. So maybe I would go for 1, 2.
So if x is 1, y is double that.
I could offer 6, 12. I might go 500, 1,000.
And if the first one was 4.5, like we had 4.5 there.
Then I think I'd go for 9 as my y coordinate.
And the first one was -2.
-2, I think I'd do 4.
The same as this one? No? Oh, no. So the question I could then ask you is, can you find a value which satisfies that criteria and that criteria? Because everything seems to be different so far.
So I think if I had 4 and 8, add up to 12. But the y coordinate, 8, is double the x coordinate, 4.
And in this case, that fell into place quite nicely because they were both whole numbers.
Yeah.
This could be a lot more complicated. The criteria could be more difficult. It could be more challenging. And in this case, representing what we've just done diagrammatically could be quite helpful. So we could have our x and y coordinates. We could represent all the numbers that satisfy that equation diagrammatically, and it would look something like this. X plus y equals 12. And it's got that slope because as x gets bigger by 1, y is going to have to go down by 1. And it'll have to go through the point 12, 0, and 0, 12. And like you said, there are an infinite number of possibilities. If I go -1,000 here, I'm going to need to go 1,012. This condition can also be represented diagrammatically. Going through the origin. I've missed the origin, but there we are. Here we have y equals 2x. And again, infinite number of possibilities. Every time my x-coordinate goes up by 1, the y-coordinate goes up by 2. And we've got the point where they meet, which is the point 4,8. And what we've done is solved a pair of simultaneous equations.
Exactly.
And understanding diagrammatically what you were doing can help students appreciate what they're doing when they're solving simultaneous equations. Infinite number of possibilities here, infinite number of possibilities here. In this case, only one possible value which satisfies both. And a diagrammatic image can be really helpful to understand why sometimes there isn't a solution.
Yes.
Because if I'd said x plus y equals 12, and then I'd said x plus y equals 15, you would have ended up with two parallel lines, and these two are never going to meet. But I might also describe this in a slightly different way and say y equals 12 minus x, for example, and all the values here also satisfy the other equation, and they overlap. And so there are an infinite number of possibilities. So thinking about simultaneous equations diagrammatically can be really helpful to students.
So we hope that's given you a flavour of this fourth stage of the process, visualising and representing. If you'd like to find out more, then you can visit the primary teacher landing page or the secondary teacher landing page, which are identically structured. If you click on this box which says Developing Mathematical Thinking, and then you can choose the Visualising and Representing link, you'll be taken to a page where you've got linked to our guidance at the top. And you can see that our guidance sets out our values and ethos with respect to mathematics and mathematics teaching and learning. And then we've identified some different ways of representing mathematical ideas, going from visual through to algebraic, and then some examples of analogous situations and analogies that you can use in the same way that we used the football teams to talk about adding and subtracting positive and negative numbers. If we go back a page, you can see by scrolling down, you get links to tasks. So they're tailored to particular year groups, all curriculum linked. So you can choose the tasks that best suit the classes that you're working with.
Having discussed multiple representations, we're now ready to embark on the final stage of a mathematical journey. So the fifth stage focuses on reasoning, justification, and proof.
Welcome to the final stage of our mathematical thinking journey. So having done some exploring and noticing, working more systematically, then some conjecturing and generalising, we've used some visual representations to help make sense of the mathematics. And here we are now, Charlie, at the final stage. So we've convinced ourselves. We might have convinced a friend. However, what about a skeptic? Mathematicians like to think about convincing a skeptic. So here we're going to have to use some rigorous reasoning to explain what is happening. So to do this, we're going to share a task with you, which is called 3 neighbours. So we're going to take 3 consecutive numbers, and we're going to add those numbers together, Charlie. So would you like to choose 3 consecutive numbers?
Okay, so 4 plus 5 plus 6. And you want me to add them?
Add them together, the total of those?
15.
15, okay. As you're watching, you may like to choose your own set and have a go yourself. Okay, another set of consecutive numbers,
And this is what
Charlie?
we would ask students to do, presumably.
This is exactly what we would ask students.
Lots of students. Well, I might try 10, 11, and 12.
Okay.
And that adds up to 33.
33. Okay. So as you say, we've got students trying their own set of 3 consecutive numbers. So we've got lots of totals. Let's try one more. Can you give us another one, Charlie, please?
Okay. 99, 100, and 101.
Fantastic. And that gives us a total of
300.
So but in the classroom now, what we might do is we might gather together some of the results on the board, and we'd go through some exploring and noticing, and students might offer some suggestions. If you've not thought about this problem before, you may like to pause the video now and then restart once you've had a chance to think. So, Charlie, I think students might initially think, oh, well, what have we got here? Have we got some multiples of 3, maybe? So this is our conjecturing, and then we might go into a more systematic phase and do some examples, maybe changing gradually, and draw on some representations to help us make sense. But now we're in this final stage.
Can anyone find an example of 3 consecutive numbers that do not add up to multiples of 3?
Lovely idea. Okay, so now we're at the stage where we are convinced that 3 consecutive numbers always add to a multiple of 3. So we could think about this in a number of different ways. Let's try thinking about it numerically to start with, shall we? So you started here with an example of 4 plus 5 plus 6. So what if we go to the next set of 3 consecutive numbers?
So instead of starting with 4, I'd start with 5.
Yep.
So it'd be 5 plus 6 plus 7.
Okay.
And the total's 18.
Okay. And what about the next one?
I'd start with 6, so it'd be 6 plus 7 plus 8, and the total's 21.
Okay, so here we've got 15, a multiple of 3. Here we've got 3 more. We've got 18, another multiple of 3. We've gone up by 3. Now that makes sense, doesn't it? Because we've added 1 to each of our starting numbers, so we can see that the total is going to go up by 3. Similarly, if we go to the next set of 3, 6 plus 7 plus 8, we've got a total of 21. We've gone up by 3 again, reflecting the fact that we've added 1 to each of the numbers that we had previously. What would happen therefore, Charlie? I wonder if we went back from this point.
Okay, so I'm predicting that the total is going to be 12 because it's going to be 3 less than that because I'm going to take 1 away from that one. I'm going to take 1 away from that one. I'm going to take 1 away from that one. And so when I add them, my total is going to be 3 less than that because it's 1 less, 1 less, 1 less, 3 less altogether.
Fantastic. So in the classroom now, what we might do is we might ask students, how would they use what we have done here to convince a mathematician that 3 consecutive numbers always add to a multiple of 3? Charlie, I wonder what you might like a student to respond to that question.
Yes. So here we might give students a chance to work in pairs, to try and rehearse what an argument might be. But eventually, we'd want students to appreciate that because we started with 3 consecutive numbers that added to a multiple of 3, and because we know that every time we go up to the next one and the next one, we're always going up in 3s, and that multiples of 3 go up in 3s themselves, you are going to always hit a multiple of 3. So we may go from that one to that one. So we're going to have to add 3, so 1 to each twice.
That's right.
So we're going to add a total of 3 and then another total of 3. If we ended up going to 104, 105, 106, I will have added 100 to the first one, 100 to the second one, 100 to the third one. I will have added 300 altogether, which is a multiple of 3. And we know that if we start at a multiple of 3 and keep adding 3s, we're going to hit a multiple of 3. In the same way that if we have a multiple of 5 and we keep adding multiples of 5, we're going to hit a multiple. So I'm beginning to think that I'm going to be able to use a similar kind of argument for when we have multiples of 5. But let's go to that later.
Okay. So this is one way of convincing ourselves, and what we've done here is a rigorous argument. This constitutes a rigorous argument for why we always get a multiple of 3 when we add 3 consecutive numbers. But we might think about it differently. What about if we think about it pictorially or diagrammatically, Charlie? So let's imagine that we're creating some images of consecutive numbers. I might like you to imagine that I've taken some interlocking cubes and I'm building a tower. So if we start off with...
How tall is my tower?
Left upstairs, that's good. Okay. I like the way you've done that, Charlie. So these dotted lines are showing that it could be even longer in the middle. This could be any length in the middle. So we're beginning to create this
I could do
generality.
Concertina kind of thing.
Nice.
We don't know quite how long that is.
Okay. So this is the smallest of our 3 numbers. Now, we know these are consecutive, so we know the second number is only going to differ by 1. It's going to be 1 more. So we could represent that with another tower.
Maybe I'll carry on with the concertina. Okay.
But it's just 1 more than the first one. And then similarly, we can represent our third number. The third consecutive number is 1 more than the previous one.
So it's like a staircase.
Like a staircase, exactly. So Charlie, we're taking these 3 consecutive numbers and we're adding them together. And I'd like to offer an image for you. Now, what I might do in the classroom is simply draw that without saying anything. And I might turn to students and I might say, so how could we use this representation, this image, to convince ourselves that 3 consecutive numbers always add to a multiple of 3? Charlie, what might we hope that students would say?
Okay, so I might... Yes, so my students, I'm going to just make your arrow a little bit smaller. I might say, okay, if I take that 1 unit and I put it here, so that no longer exists, the total of my 3 consecutive numbers must be the same as the total of these 3 identical numbers.
Absolutely.
And when I add 3 identical numbers, I get a multiple of 3. If I add 3 10s, I get 30. If I add 3 12s, I get 36. If I add 3 5s, I get 15. If I have 3 identical numbers and I add them together, I get a multiple of 3. The 3 consecutive numbers added up to the same total.
And in fact, this image offers us, I think, a slightly deeper insight than perhaps our numerical proof did. Because I think what we're seeing is, if we add 3 consecutive numbers, the total is going to be a multiple of 3. In fact, it's going to be 3 lots of the middle number.
And we can go back to our numerical examples. That was 3 4s. That was 3 5s. That was 3 7s.
In fact, I think that might have been how you were calculating the totals, Charlie.
That is why I chose 99, 100 and 101 to make my life easy.
Okay, so this is an alternative representation which is watertight reasoning and offers slightly greater insight. So let's think about another representation. Some students, as they get older, will be introduced to algebra, Charlie. So how could we represent the sum of 3 consecutive numbers algebraically?
Well, I might use algebraic expressions to represent your 3 columns.
Yeah.
So if the first column I represent by the letter A, the next one you said was 1 taller.
That's right.
So it's going to be A plus 1.
Yep.
And the last one was 2 taller than the first one. So I've got A plus 2.
Yep.
And we added them all together. And we get 3A plus 3. Now this again uses some of the insights from here. This is a multiple of 3.
Yep.
And if I add 3 to a multiple of 3, I hit the next multiple of 3. So that convinces me that the total is a multiple of 3. Some people like factorizing, and that's the same as 3 lots of A plus 1. So A plus 1 is our middle number, which is what you were talking about earlier. And the total is 3 times our middle number. 3 times something is going to be a multiple of 3. So again, I've got a convincing argument that the total is going to be a multiple of 3. This is a different way of expressing what happened here, but it seems to me both are equally valid.
Absolutely.
Sometimes we give high priority to writing something algebraic, but in this case, this gives the same amount of insight and is just as convincing as that is. I suppose what I like about this is not only that if we've been on a mathematical journey exploring 3 consecutive numbers, conjecturing, and eventually coming up with a justification, a reason, a convincing proof, is that we can then adapt this and get students thinking about 5 consecutive numbers. Are these 3 arguments still valid when we've got 5 consecutive numbers, or 7 consecutive numbers, or 99 consecutive numbers? We want students to be really good at being flexible at using these very powerful arguments in a variety of ways. My answer is yes, all these ways of convincing ourselves can be used for 5, 7, 99. But again, with a little bit of adapting, one could start thinking about 2 consecutive numbers and 4 and 6 and 8. So an even number of consecutive numbers. We've started with an odd number of consecutive numbers because it's easier, because there's always 1 in the middle. You can imagine 5 having 1 in the middle and 2 on either side. 99 having 1 in the middle and 49 on each side. You can imagine what happens there. With an even number of consecutive numbers, it's a little bit trickier, but in the way that we talk about low threshold, high ceiling tasks, there's a slightly, harder challenge to think about. And of course, one could, I think, think about an odd number of consecutive even numbers or consecutive multiples of 5. Or, there are variations. And testing arguments to destruction is quite useful. Which argument would you use? Which model is more helpful? getting students to think about when would they use one and when would they use another seem really valid discussions in the classroom.
Absolutely. So we've used this three neighbours problem to illustrate the ideas behind reasoning, convincing and proving. But if you'd like to find out more, then do go to our website. You can choose the primary teacher or secondary teacher landing page. They're both structured in the same way. If you click here in this box, which is titled Developing Mathematical Thinking, and then you scroll down and choose the reasoning, convincing and proving link, you'll find a link at the top in the blue box to our guidance. We set out our guidance. At the top, we describe our values and ethos, so what we believe about mathematics and mathematics teaching and learning. And then you can see we've illustrated our ideas. We're a number of different problems, in addition to three neighbours, which we've demonstrated for you today. If I go back a step, you'll see by scrolling down that we've also linked to groups of tasks. So these are curriculum-linked tasks for particular age groups. So we hope that you'll be able to find the tasks that best suited to your learners with whom you're working at the moment and help them get better at reasoning, convincing and proving.
We hope that this final stage captures some of the sort of pleasure, satisfaction of going on these mathematical journeys where you start uncertain about how you're going to proceed in this kind of messy kind of way.
Fumbling
asking
in the dark.
questions, but eventually sort of seeing the light and eventually having really nice explanations that help to make sense of it. We want students to appreciate why mathematicians enjoy working mathematically, the pleasure that comes from making sense and being able to understand why things happen, and then capture with very powerful images or abstractions the generality of what's going on. There is great pleasure in reaching this stage, and I hope your students enjoy working on some of the NRICH problems that we've identified that are suitable for developing these mathematical thinking skills. So we hope that you found it interesting to travel along with us along our problem-solving journey, starting by exploring, going on to working systematically, conjecturing, thinking about visual representations and multiple representation, and eventually to justification and proof. We hope that this is the kind of mathematical journey that students have the opportunity of traveling along so that they can work like mathematicians and not just learn new procedures. Some mathematicians talk about how it wouldn't be good enough just to go to music lessons and learn how to read mathematical notation and practice your scales if you never actually play some real music or join an orchestra or sing in a choir. And likewise, you can learn how to serve and volley in tennis, but if you never play a tennis match, the whole thing is rather dry and abstract. We want students to have the experience of working on problem and tackling them in a confident way, appreciating what knowledge to draw on, but also what skills to draw on.
We hope also we've given you a way to explore the NRICH site further for yourselves. So you can look at the guidance we've created on each of the mathematical thinking skills and find tasks to suit the students that you work with in your classrooms.